Hi, welcome to this video, and in this video I'm going to talk about how to convert a screen printed carbon electrode into an immunosensor. I do have some technology in front of me, and I will be talking about specifically the conversion or fabrication of immunosensors on top of these screen printed carbon electrodes. They're called 501s from Zimmer and Peacock. With that said, let me shoot forward, though I would say that some of the materials that I'm going to present will sort of be more generally applicable as well. So what I will describe is the taking of a carbon electrode, activating it with extra carboxylic acids, activating those carboxylic acids so they become what called active esters, reacting that with streptavidin. I should sort of jump in quickly and say that streptavidin is a good strategy when you're trying to make immunosensors, because there are probably tens of thousands of antibodies available in various catalogs from various suppliers, and they're often biotinylated, and therefore if you make your screen printed carbon electrode streptavidin functionalized, then you've got a good conjugation. You can achieve a good conjugation between the antibody and the surface through the streptavidin biotin let's say reaction or coupling. So you can take your antibody, which I'll also describe in this, which is biotinylated, and then that will have a good reactivity with the streptavidin and will conjugate your antibody to the surface. I should also add that I will talk a little bit about how to measure these immunosensors once you've actually made them. So at some point you will have functionalized the sensor. That's, I would say, your manufacturing step, and then there'll be the kind of reading step where you actually put an antibody and you can look at the kind of binding of that, not antibody, so you can put the antigen into that or onto that surface of that sensor and read that binding using something like a sort of soluble redox reporter. The reason I'm suggesting this makes for an easier assay than necessarily doing what's called a sort of sandwich assay, where you kind of have a secondary reporting antibody with HRP attached to it. Those don't lead to low cost, easy to use, rapid sensors. Many times when people are trying to make things on things like screen printed electrodes, they're thinking about point of care applications. And point of care applications, they will say, oh, I want it, it's got to be low cost, it's got to be rapid, it's got to be easy to use. Well, once you start making the assay a bit more complicated and just having a more traditional sandwich type assay is already adding complexity and will add cost, and it won't necessarily be that easy to use, and you won't be able to just roll it out into the kind of field as readily as the simple assay that I would probably try to describe here. I'm also, side note as well, that I'm talking specifically about carbon electrodes today. Obviously there's lots of literature on the use of gold electrodes. At ZP we do provide gold electrodes, and with gold electrodes people often use self-assembled monolayers where there's a kind of a thiol that will attach to gold, and it is a good coupling chemistry. The only thing is if you look at the price of gold versus the price of carbon, you'll find out that gold is 28,000 times more expensive than carbon. So when people talk about I want a low cost, easy to use, rapid medical diagnostic, well, the low cost and gold don't necessarily go well together. Why? Because gold is a material that lots of people want for many applications, both luxury goods, but also then kind of science and engineering products, whereas carbon is much more kind of readily available, and there's not such a sort of competitive market for carbon as there is to gold. So if you want to tick that box of low cost, then I would definitely recommend carbon over gold, just simply any day. I will describe that we'll take a bare carbon electrode. I will highlight the fact of reproducibility. Something that's really holding people back is there's really two sources of screen printed carbon electrodes these days. There's I say vendors or manufacturers like Zimmer and Peacock. So we are one of many, though I would say that we make the most reproducible screen printed electrode out there. Why is it that we achieve it? Because actually we use these screen printed carbon electrodes in many of our products. You'll see them in our food sense technologies. You'll see them in our new lead assay. So we do use these electrodes a lot ourselves, and therefore we need them to be reproducible in order to benefit our customers. And at the same time, then we make them available on our web stores for the academic market and also for the startup market. So I'll talk about the carbon electrodes. I will talk about how we're going to get the streptavidin onto the surface. I'll talk about the coupling with biotin. The biotin is, or rather this strategy of making immunosensors by coupling or functionalizing a carbon surface with streptavidin and then using a biotinylated antibody is a good strategy, because then you can leverage, there are lots and lots of suppliers of antibodies, and lots of suppliers of antibodies are actually making biotinylated versions of their antibodies. So you can really leverage that, let's say those catalogs, and find an antibody specific to the antigen or the target that you're in particular interested in. Now the procedure I'll describe this afternoon, or rather in this video, is kind of, it's easy enough to do. The instructions are quite straightforward. It doesn't really take more than a pipette, carbon screen printed electrodes, and a potentiostat. Obviously I'm super biased. I do have a potentiostat in front of me. This is the Sensi All potentiostat. In fact, I've got it in square wave voltammetry mode at the moment. The reason I bring that particular one up is because what we're most interested at ZP is not just the kind of lab experiments, but also turning electrochemistry, let's say, into actual products. And this is one of the few potentiostats that actually is also able to go into a sort of a minimally viable prototype mode as well. So you can actually use it for demonstrating to potential investors as well. With that said, let me go back to the slides themselves. So I do like the idea of functionalizing a carbon screen printed electrode with streptavidin, because then you can leverage all the antibodies that are in the catalogs, and they often come biotinylated. I'll also talk about the testing and measurement at the end as well. I do have lots of videos where I sort of talk about the reproducibility of ZP screen printed electrodes. We definitely have put, constantly, whenever we make screen printed electrodes, we're sacrificing good numbers of the electrodes to just check that they actually are reproducible. So just know that if there was ever a problem with a batch of screen printed electrodes, you'll often find that in fact the first people to discover it are actually let's say the paying clients. But in ZP's case, the first people to discover whether there's something wrong with a batch of screen printed electrodes is actually ZP, because they'll be coming straight off our production and start going into our own products or going into paying client programs. And so we have many mechanisms in order that we would actually prevent, let's say, poor quality material ever hitting the open market. So what you buy off our web store is really some of the best screen printed carbon electrodes out there. And that means we can rapidly make assays, and you will find out that ZP actually does have a whole range of assays and products, all using electrochemistry and all using our in-house manufactured screen printed electrodes. As I've described already, I will describe that we're going to add carboxylic acids to this carbon surface. I will talk about activating the carboxylic acid using EDC NHS coupling. I will talk about then reacting that with streptavidin. I will then talk about go to a catalog, find the antibody that you like, make sure it's biotinylated, and then you can couple that biotinylated antibody to the surface. At that point, really, you've kind of fabricated your sensor. I'm using the word fabricated because what this procedure is really fabrication. It's not manufacturing. Manufacturing is a multi-million-dollar effort. You've got to get all your standard operating procedures in line. You've got to manufacture, you've got to find out what the problems are, you've got to work out the reproducibility, you've got to work out how robust your manufacturing process is. But this is really describing a process for fabrication of some I don't want to say prototypes, but some manufacture some functional electrodes. So once you fabricated it, then you can start bringing your actual target antigen in, which will bind to the antibody, and then we can read that binding using a soluble redox reporter like something like ferricyanide. So preparing the surface, the first thing that we're going to do is take our carbon screen printed electrodes, add something like CMD, carboxymethyl dextran to the surface, which has got lots of carboxylic acid group, CO2H's on it. And we can do it just by adding something like 3 microliters. In fact, just adding 3 microliters to the central circle here. Sometimes in the literature people are a little bit ambiguous about it, but there's no point in putting material anywhere on this other than where you want it. I do see people flooding these things with material. A, it's a waste of material, and B, you don't want to be putting things like antibodies on your counter electrodes. It can end up essentially blocking your counter electrode, and you do want the counter electrode to be able to sort of function as a current carrier for what's going on in the working electrode. So A, preserve material by only putting it on the circular electrode, and B, you really don't want to be putting things like antibodies on the counter electrode. It's almost, how do you put it, pointless. So CMD is nice and easy. 3 microliters at 50 mgs per ml should do it. When I say, I'm going to share my screen again. I should say that this is a very generic kind of formulation. You have to tweak this, but I think it's giving somebody a starting point to where they should actually start with. We may leave that standing overnight, so you do it at the kind of end of your day. Don't do this one at a time. Do this in parallel. Do 20 electrodes at a time, and leave it standing overnight. Most of that material will be evaporated off anyway, just leaving a surface of CMD. Wash it. Wash it by just putting something like 50 microliters at the end of the sensor of PBS, phosphate buffer solution, probably pH 7.2, and taking it off with a pipette. Then you want to activate the electrodes. So adding in a solution of EDC NHS. You will have prepared these stock solutions of EDC and NHS, just mix 50-50 in a MES buffer, MES at pH 4.7, and then put 3 microliters of that again on the circular electrode. Same theory as before. There's no point in putting excess material on anywhere where you actually want to do it. I think it's obvious, but I have seen people just sort of flooding these electrodes with all sorts of materials. Excess material. It's just a waste for a start. EDC NHS is quite active. It will be reactive, so you kind of want to leave that standing for about 10 minutes. And then you're ready to do your Streptavidin. So take off the EDC NHS with the pipette. It's only 3 microliters, so probably after 10 minutes, most of it's evaporated anyway. And then you're ready to add in your Streptavidin. Again, 50, well, not again, this time it's 50 micrograms per milliliter, and leave that on for 60 minutes so that it can, let's say, couple with the now activated carboxylic acids. And it should sort of couple on. And then again, there's a wash step. Again, this wash step's not putting it under a tap and just leaving the tap running on it. I mean, we are being quite gentle here, but we're adding 50 microliters of buffer and taking it again off with the pipette. The next step is quite straightforward. I think Streptavidin and biotin, sort of love each other. So take your antibody, which you will have prepared in quite a low salt concentration of PBS, put it on there and leave it standing there for 60 minutes. You can, when you've done that, sort of take it off with a pipette tip. But again, after 60 minutes with 3 microliters, to be fair, you're not really going to have actually much to take off. It will all have evaporated. You want to kind of make sure that there's no active esters left on that surface, so you kind of end up reacting those with ethylamine chloride, just to kind of, neutralize that active surface at the end. Incubate that for 10 minutes while you do that. Again, I'm always using the word 3 microliters, so you get the idea that I'm always adding it to the circular electrode, and then wash it again with PBS. I would actually use that sort of 0.01 mole of PBS at that point. Wash it by putting about 50 microliters onto the end of that sensor and taking it off with the syringe as well, being fairly gentle. And then following, now for each step, each time you do let's say one of these steps, you can actually follow whether you're being successful or not by actually looking at cyclic voltammetry. So we would, for example, one of the first steps here was we had a kind of bare electrode, and then we added that dextran to it. And what you should see is actually that the voltammetry becomes quite how do I say this? Becomes quite distorted, because you're essentially blocking the surface. And then we would sort of basically test it with something like a bit of ferricyanide using cyclic voltammetry, just to see that we actually had modified the surface. If we find out that the electrode still looks like a bare electrode, then the simple conclusion is that, in fact, for some reason, the functionalization step didn't work. And by the time you get up to the antibody, the surface should be really quite blocked. And so the ferricyanide should show a very distorted voltammetry by cyclic voltammetry. What I'll do is actually, I'll just do a quick... The nice thing about this particular potentiostat, I'm just going to do a quick show. At the moment, I'm in square wave voltammetry. I just want to go into cyclic voltammetry. So I've got these series of QR codes. These QR codes are what really allows you to actually turn this, what's a potentiostat, into a minimally viable prototype, something that you can actually show to investors or sort of demonstrate to funders that you've actually developed something that's actually quite translational. There we are. I've gone into cyclic voltammetry mode. I just scanned the right QR code. We've also got EIS on here, electrochemical impedance spectroscopy, which is also quite a good technique for reading immunosensors as well. I think square wave voltammetry and EIS are the two best methods, can I put it that, for looking at electrochemical immunosensors. But when you're actually just following the process, cyclic voltammetry is kind of quick and easy to do. I'll just put some ferricyanide on the end of that. I'll just go ferricyanide 66. I will go continue. Yeah, this will give me quite a distorted CV, but I just want to do a quick let's say experiment for you. In fact, what I've done is have I closed it? Yeah, I have actually closed it. Yeah. So it's just gathering a CV for me now. This is a very, obviously I'm super biased, but a very unique kind of instrument. It's very cloud enabled, which means that any kind of data that we gather ends up going immediately to the cloud. And this is really advantageous when you're when you're developing. You can always answer the question, where is my data? It's not locked away on somebody in the lab's laptop. It's actually all just immediately gone to the cloud. So it's very good for you as a, if you're the CSO, the Chief Scientific Officer, and you're trying to kind of follow what's going on, you can actually just remotely log in and actually see what's going on in the lab, let's say. And it's also very useful when you're actually trying to roll technology out to, let's say, hospitals, etc., and you want to kind of see what's going on. I'll just do a quick refresh here. Like I said, I just did that real quick, and I did it quite a fast scan rate, but I can see the CV here. I just need to increase my my current range a little bit so I don't cut it off. But I just did a quick CV on there, and you can see that immediately. Drop a solution on the on the screen printed electrode, ran the CV off my phone. We saw the data coming in real time. The data went back to the phone, and then the data immediately went to the cloud. And if you find other videos on ZP, or see us using this workflow in actual client-facing products. And I don't mean just for the R&D market, I mean for things like the food and beverage industry. Anyway, back to the point, which was you can follow these functionalization steps by cyclic voltammetry. Quick and easy to do. If the CVs are not getting distorted, then you're probably not functionalizing the surface. Reading an electrochemical immunoassay. So having functionalized the surface with Streptavidin and then done the final functionalization with the antibody, you've essentially formed your sensors at this point, and then you're kind of ready to start reading the binding itself. So I'm showing here the idea of proteins or just antigens that are binding to the respective antibody. And I'm showing here the idea that you could report on this using something like ferrocyanide. Now you will have to optimize this because if you're trying to bind something that's quite big, when I say quite big, let's say a virus, or let's say a microbe, then those are quite big, and if they're at quite high density, then in fact it's quite easy to read their binding because they're essentially blocking that surface quite readily. Now if you're doing something smaller, small molecules very hard, small proteins, not so hard as small molecules, and not so easy as as a macro microbial something like something like a Streptococcus aureus or something like that. So you may want to play with how much ferrocyanide is in there, but a good sort of starting point is potentially 5 millimolar, 1 millimolar, 10 millimolar. Though I think this is a kind of a bit, everyone sort of seems to use those concentrations, but in reality, you would, if you add too much ferrocyanide, for example, you'll end up just swamping this binding event, and you don't really see any changes. But as you reduce the ferrocyanide, then you'll probably become more sensitive. So that does need a little bit of playing with. But doing an assay this way is an easier way. The other way of doing it is to do more like a sandwich assay where you have a secondary antibody with HRP, horseradish peroxidase, on it, and that ends up giving you your signal. But that just adds complexity. So these kind of simpler assays are at least our recommendation. You can read the degree of binding of your antigen to your antibody using a technique like square wave voltammetry. So in fact, I'll just show you very quick. At the moment, I was using the potentiostat for cyclic voltammetry. I'm just going to turn on my QR reader and go over to here, and now I'm in square wave voltammetry, so I can actually do something like a square wave voltammetry measurement if I so wished as well, which I've just started in fact. So square wave voltammetry, I don't want to come off topic slightly, but EIS is also not a bad technique actually, and this device does also have EIS as well. In fact, I've got the QR codes all a little bit too close to one another, and back there we are, I've got EIS there as well. So I'll go back to the slides, which I will do here, and now the technologies I've been using, it's easiest. The procedures I've been describing are fairly generic. You would change the volumes depending on the screen printed electrodes that you were using. Obviously, it's much easier for ZP to give video support, which we do. We do a weekly webinar where we actually answer technical questions that have come in during the week. We generally do that for free. If people are commercial, like large companies, they generally don't want us to be doing that, and then they engage us in actual direct support, because we do have ISO 13485 contract development, contract manufacturing facilities, but it's quite, you can appreciate running a full-time team doing this kind of work is an expensive endeavor. But if you need to do this heavy lifting yourself, there is a potentiostat. It's called the Sensi-All potentiostat from ZP. It's a very elegant, and obviously again I'm biased, potentiostat. I don't think there's anything actually quite like it on the market. People don't understand that these kind of slot-in potentiostats are really a real pain, because most doctors, nurses, let's say people outside of the scientific community, trying to slot something in is a real nightmare. You don't need to slot this in. You just click that up. There's no chance of getting ingression of liquid. Slots are a bit of a nightmare actually for real people, because they end up putting solutions through the slots and into the electronics. So we do have a very elegant way of putting electrodes in and out, and that keys in quite nicely and just closes it up like that. So I do obviously think that's quite a nice feature. And I will also link to these carbon 501 electrodes. It's just a circular design, makes them easier for people to rapidly fabricate with. And then if you do have any questions, we do a weekly webinar, and I hopefully on my next slide I've got a contact us as well, which I'll also put underneath the video as well. So in summary, I've tried to describe a procedure for making electrochemical immunosensors on a screen printed carbon electrode, and I've been deliberately trying to give you a fairly easy procedure, an easy assay on a low cost substrate, because then it will kind of tick those boxes of everyone wants a low cost, easy to use and rapid systems, especially for point of care. And I think the things I'm describing here will actually allow that to be achieved. If you have any questions, please don't hesitate to reach out to us. Okay, thanks very much.